Good afternoon, everyone, and welcome to the webinar on next generation metal printing. Today's presentation will be the WLAM simulation module of AM PravaH, and I will be conducting this webinar. Let's introduce the company and the founder briefly. So, Mr. Advait Gupta, who is the Stanford University alumni, who founded this company, Paanduv Applications, in Bareilly, Uttar Pradesh, in year 2020, and have developed, licensed, and maintained AM PravaH software, which is the proprietary software for additive manufacturing processes. The office is located in Bareilly, Uttar Pradesh. Uh, you can reach out to us at the office address. It is nearby the capital of India, New Delhi, and you can reach out to us at the given address. A brief introduction about me. My name is Pratik Patange. I've done my MS at RWTH Aachen University in Germany, where I studied material science of metals. And I have some previous experience working with LPBF and powder DED process called EHLA. Currently, I'm working at Paanduv Applications as a research engineer and developing AM PravaH software. So currently at AM PravaH, we have three processes: LPBF, WLAM, and WAM. WAM is under development. You will be hearing about that from us in coming months. And in presently, the LPBF and WLAM modules are active in our software, and most of our past partners are actively using it for research and development purposes. So to begin with, I just want to give a small animation about what the WLAM process is. In the animation, you can see like a wire feed is getting melted by laser, and there is a droplet forming. And to simulate this, we have the AM PravaH software, which is uh, like physics-based CFD solver, which accurately represents the droplet formation and its movements. So let's just move on with the introduction of the WLAM process. It is the wire laser additive manufacturing. Some people call it laser wire additive manufacturing or wire DED process. Like it depends on which region of the world you are from, and the name that you give. But the core concept of the process is same. The energy source that we use is the laser, and the raw material in the form of metal wire is melted mid-air and let it fall on the substrate or the previously developed uh, layers of materials, and the 3D design structure that is tailored for the given applications is then formed. So I would like to show some animations regarding how the process works. Here you can see a small build, like a cube formation is taking place. Most of this work is done at research institutes to see how the defects are present in the process and how to eliminate that using process parameter optimization. Once you have a correct set of process parameters, you can then move on to building 3D parts at a large scale. So for LPBF process, you are limited by the size of the powder bed that you have. But here you have the freedom of choosing large parts and build it using complex robotic systems. And at AM PravaH at Paanduv Applications, you are using AM PravaH to simulate the tracks, isolated tracks, and decide the process parameters which you want to use in the actual process. So let's understand the working principle briefly. Here is the schematics. Here is the schematics of the whole process. We have a laser head that provides us the laser. Then we use optics to focus all that laser energy to a particular point. We use a shielding gas to avoid any oxidation that can occur during the transformation of the solid to liquid, and then again with solidification from liquid to solid. And we can avoid many defects by providing a shielding gas which is inert in nature. There is also a lateral wire feeder that provides the raw material, that is the metal wire that we use, and layer by layer we built the whole part. So zooming in, you can see interaction of the laser with the feeding material and also with the substrate or the previously uh, developed layers. So the working principle that is involved in this process is the phase changes that occur, like from solid to liquid, and then again with solidification it is converting back into a solid, and it is changing a lot of the material properties during this process. There is the laser dynamics that is involved, like how the laser interacts with material. It's not the same for every material. uh, like it depends on the composition that you have in your alloys uh, to see if it's weldable or not. There is mass and heat transfer that is occurring here, and temperature dependent surface tension. So the melt pool has liquid metal, and depending on the temperature of the melt pool, there are some other forces that are acting on that define the whole solidification process. And then comes the Marangoni convection that shows like how the melt pool is not just a steady state, it's actually evolving state where liquid is swirled around, and it's transported from one point to another, like in a very small area and volume. Here you can also see like how the Marangoni convection is also simulated using AM PravaH. Now moving forward with the current trends of WLAM in industry and research. Uh, it is a sustainable technology that is catering towards Industry 4.0. Uh, it's also focusing towards reducing material wastage that can also help in circular economy. It is achieving near net shapes that are dense in nature, and with these facts at hand, we can produce large components. And in the end, like it's a 3D manufacturing process, so we have a greater freedom of part design, and we are not limited by the conventional manufacturing processes at hand. We use wire feedstock, and this allows high deposition efficiency and high deposition rates. It allows a really good transfer of energy to the substrate, so that we have a metallurgical bonding that is with the substrate and the deposit. Then there is smoother melt pool dynamics which give us a stable microstructure, and in the end, with all of this combined, we have a robust component at hand. uh, I can show you some process like use cases of the WLAM process. Mainly it is in the R&D. First we have to see if the process is scalable or not. For that we have to do a lot of research and development. As you can see, there are some tracks that are formed to see how defects can be formed, how to eliminate that, how to come to a better set of process parameters, and then use it for scalability. Some industry applications can be, for example, as a propeller or a small gear wheel. Here you can see in the examples the formation of a gear wheel with cam can be done, and then after post processing you can directly use these wheels as is in other applications that are relevant. And the most important aspect of WLAM can be in repair applications. So there is the high demand of tools that are used in, let's say, uh, forming plants, where the forming tool loses its life because of the wear and tear that is happening on the tool. So to avoid this small life cycle of a tool, we can use WLAM to actually extend the whole life cycle of a tool. It will be better for efficiency, it will reduce a lot of wastage, and it has a sustainable future. Along with it, there are some applications in gas turbine blade repairs. The microstructures in gas turbine blades is very critical, and with LPBF or WLAM process, uh, we can actually cater to these microstructures and actually have advantage towards attaining a really reliable microstructure. So what is next gen manufacturing? So as I've previously shown you some examples, we right now also have some other examples here to show, like a propeller or a like a rocket thrust chamber that you can produce, and obviously there needs to be some surface finishing to be done on most of the parts. If there is some aerodynamics involved, or the interaction of fluids with surfaces is involved, in that case, uh, finishing like surface finishing is definitely required. Apart from that, uh, we can form like curved pipe structures. Now these look very simple, but as an from the engineering perspective, these curved surfaces are really difficult to actually manufacture. So the casting can be done, but with this process with WLAM, we can do this more reliably, and we can have a near net shape in the end. So what's special about the next generation manufacturing is the hybrid manufacturing. So combining additive and subtractive manufacturing will give us this new hybrid manufacturing. It is not a new concept, it's widely known, it is old, but at present this is relevant. With this, we can move towards modern manufacturing techniques where we have a reliable part that is built using additive manufacturing, and then the precision parts are then used to produce the components that are like exactly uh, as the customer needs. Now, placing AM PravaH in this next generation manufacturing is a task that we have at hand. So WLAM is a process with high deposition rates, and we can build really large parts. Uh, it's like really efficient in using complex alloys, so it is already reducing a lot of wastage, and many of the complex alloys are initially very expensive, so it is cutting a lot of cost in the process. There is a stable heat input and stable melt pool that allows us to build robust structures, and exploiting like new like modern systems in robotics. We can actually incorporate everything in hybrid manufacturing, and this can lead to novel alloy designing of next generation additive manufacturing. And here at the forefront, we are at Paanduv developing AM PravaH that can be utilized for new alloy development. So as soon as we have a desired material composition, we can use AM PravaH to fast track the process of alloy design catered solely for WLAM or other additive manufacturing processes. So I would like to just give a brief roadmap of like what the next generation manufacturing can look like. It can be a digital twin. We can have a digital like a virtual twin of the machines and monitor everything at all the times and have all the data to redevelop everything at a faster track. Then comes hybrid manufacturing, as we have discussed before, and circular economy, that's also there. So all of these have one thing in common, and that is sustainability. So if we begin our whole process with physics informed simulations, we can move towards rapid fabrication, and when that is established, we can move towards scalability. Now whenever we have a scalability, we have a lot of different tasks at hand, that is repair or modifications, that can also be done using these simulations as well. So we have we're trying to form this loop, and we're just trying to fit into this the first step in sustainability by providing a physics informed simulation. So what role the physics informed simulations plays in reshaping the manufacturing? So we have simulations. uh, so what we can do is reduce the trial and error. So if you already have a system and really don't know about like how to do additive manufacturing, you can try different process parameters, and uh, with like one failure after another, you can eventually reach to a really good set of process parameters. Or you can use statistical analysis methods like a design of experiments to reduce doing like thousands of experiments to like 50 or 60 experiments. But this takes time, this takes energy, and all this effort can be narrowed down by using these simulations. This is backed by the physics that is involved. So all the physics is translated into a mathematical equation that gives us the output that actually is really really similar to the experimental validations. And in the end, like if we are using simulations, we are not using any material, so there is less material usage and uh, less material wastage as well, since less number of experiments are performed to decide a set of process parameters. So using AM PravaH, we capture complex multiphysics across different phases. It is a precursor to advanced manufacturing. We can also incorporate AI in the future as we develop this software, and have a better clarity on how to uh, decide how to optimize process parameters. And we have reliable predictions. For that, I would like to show you some examples as we move forward in this presentation. So the capabilities of AM PravaH are many. So with AM simulations, first and foremost, we have process parameter optimization, which is the first step into getting the whole system set up. Then we have defect predictions, which comes in really handy whenever we are working with newer materials or different scan strategies, for example. Then there is material innovation, microstructure, or part scale modeling that will be coming up as we develop the software as well. But in this presentation, I would like to focus more on to process parameter optimization and the defect predictions. So the first thing is like the narrowing the process parameter window. We took the example of a titanium 64 alloy and used the feeding angle of 90 degrees of the wire of radius 1.6 millimeters, and used a large laser spot diameter of 7 millimeters. We deposited a track of 100 millimeters to see like how the process parameters change these results in the simulation. So with the combination of laser power or scanning speed, in this case the feeding speed, we have a narrow window of the combination of process parameters where we do not have any defects, and any variations in these process parameters can lead to like defects like lack of fusion or porosity that is not desired at all in any industry. It just leads to failure, and no one wants that. So achieving this process parameter window is crucial in every additive manufacturing process. So we took three cases where we simulated the same material for 1800 watts, 1200 watts, and 3800 watts to see like how the simulation results will come out. So the first case was the 1800 watts. As you see in the animation, there is the track development and the cross sections along the track, like laterally and perpendicularly to the tracks. and you can see like on the right side of the animation, the density function shows a clear variation near the substrate and deposition. So what that might be is first question that we can ask. And we think that it's a delamination or lack of fusion, like as a possible defect in this isolated track. To see like if this is actually a lack of fusion, we have some uh, measuring tools that we use, which I will show you later, that will clarify if this is actually some sort of a defect. So as we increased the laser power in the second case, you can see there is no clear boundary, like there is no variation of the density function near the substrate, like between the substrate and the deposition, uh, like in both cross section views. And this is like a form of a sufficient fusion of the melt pool with the substrate and this is giving us a reliable deposition. uh, we just wanted to have a third case where we increased the laser power even more by 1000 watts, and this gave us a different simulation result. Here we have proper fusion, there is a proper metallurgical bonding, but there is some defect that is present, and because of the large energy that is being transferred into this process, the slower cooling is we are getting, and we are having a non-uniform track deposition that is not really desirable in many cases. So to analyze like what this can be, like through this cross section, you can see the lack of fusion that can be there. In the case of perfect fusion, you can see like a boundary between a deposition and the substrate, and the presence of a small heat affected zone right at the boundary of the both. And in the third case, there is a defect of not proper solidification in the end. This can be named as a dripping defect in some cases, and or just a balling up case, and this is not actually desired. So less power is giving us less no fusion, and the fusion between the deposit and the substrate, and the more power is giving us a different defect that we do not want. So we can narrow down and see like, okay, between the power of ranges 1800 to 2800 watts, we can simulate more and see which is a really good set of process parameters, and then do experimental validation on that to see like the temperature profile across the domain. We can put we can put a probe right near the substrate's surface to monitor the change in the temperature. Through this we got, in the first case we got the temperature that is 1600 kelvins, which is less than the liquidus temperature of titanium 64, which is 1878. So this gives us more reliability and more facts about okay, we are not reaching proper melting of the substrate, and that can be a reason why there is no proper bonding in the first case. In the second case, the temperature at the given position is 2000 kelvins, which is much more than the melting point of titanium 64, and in third case it is even more. So we can clearly now narrow down that okay, there is not enough melting that is happening of the substrate, which is not allowing the melt pool to actually fuse together with the substrate. Furthermore, we can have some observations on the deposition tracks. So the first case shows a really good deposition. It's uniform throughout the 100 millimeter track, but because of lack of fusion, we cannot use it. In the second case, although there is proper welding, but there is less uniformity in the deposition. As you can see in the beginning, there is much more volume that is there, and it is losing some of its volume. So the deposition volume is changing a little bit towards the end of the track deposition. This can be eliminated by further doing some more simulations, and then can be validated directly through experiments. In the third case, we have looked at the temperature profile across across the region where the melt pool was not solidified in the end of the simulation, and here we can see the thermal gradient is not that much high, uh, resulting in slow cooling, and this is not desired, as it can also lead to cracks in the final build. So having uniform deposition is key, and clearly through these simulations now you can see we can actually have a set of process parameters that are simulated before doing any experiments, and see in the end like how it fast forwarded everything, from choosing the process parameters and having a final like proper track that you can use for multi-layer or multi-track depositions. There are many scan strategies that you can use. We have just shown you some examples here. It's up to the customer, it's up to the researcher who wants to develop like have the deposited 3D structure, the whole, or just want to try the different layers deposited and do some research on that. So there is set pattern for multi-track simulation. We can have L track or multi-track simulation, uh, and in the last animation you can see like a paper phase that is also coming out of it. So in some cases, depending on the chemical composition of the material, like vaporization can be one of the factors, and through these simulations through AM PravaH you can also have a visualizing aid towards like finding out the reasons why there are failures in deposition. Then there are some defects that are already like tested by many researchers, and that can also be shown in AM PravaH. Like vapor entrapment, you can see a small bubble that is uh, inside of the melt pool. There is grooves that are present depending on like the Marangoni convection and solidification rate. uh, Material solidifies at a different rate, and this can lead to formation of these grooves. There is droplet liquid transfer, like right in the beginning of the presentation I have shown you the droplet transfer that is happening because of lack of power, uh, lack of laser power maybe, and this simulation actually predicts everything from this. And there is also one defect like a hump that is that can be considered as a non-uniform material deposition, that is actually also shown through the results of the simulation. So the outcomes from the study uh, can be backed concretely, like the AM PravaH software is actually backed by the physics solver, so we can accurately predict the temperature variations across the domain or at a particular point. We can predict lack of fusion that is happening through like by looking at the density of the build, or looking at the temperature variations, and we can also see the droplet formations. Obviously all this has to be experimentally validated, and experimental validation has already streamlined the process for existing materials. So we already have a material database that is extensively tested, um, and it can be incorporated by any industry or any researcher who wants to study a different thing by existing materials. And for like rapid alloy development of new alloys, this can be a valuable asset in fast forwarding the research that the researchers are doing, or fast forward the businesses to actually have a product at hand in a limited time. So what AM PravaH is in a nutshell, so it can analyze melt pool dynamics in WLAM, uh, the metal deposition prediction along with the thermal profile can be predicted, and obviously defects and porosity predictions are there. So the benefits of the process are like from wire to part scale simulations can be done. So for now you can do some simulations for the tracks, multi-layers, and moving forward with further developments at AM PravaH, you will have like an FEM model that you can track back to at a part scale and test the materials. This is actually cutting a lot of costs, uh, like the cost cuttings by 67% in the initial optimization process can be estimated, since we are not doing any experiments and only doing simulations to uh, to determine the process parameters. It is saving a lot of material costs, so you don't have to do any experiments right from the beginning. It saves time on experimental trials. You don't have to do a lot of extensive testing on many like failed trials, you can say. And you can set AM PravaH as a digital twin in additive manufacturing, and this will facilitate further growth in this in WLAM environment. So currently we have some AM PravaH users. There are many partners that are presently in India and across the world who are using AM PravaH for doing more research. Uh, Here is the list of all these partners. Uh, there will be some upcoming webinars where we will cover up the scaling up precision of large scale LPBF simulations using AM PravaH. There will also be a module for microstructures for WLAM, and we are actually developing it, and you will hear about this in upcoming months. So I would like to thank you very much for your time, and yeah, this is the last animation that you are going to see from this presentation. Okay, so moving on, I think there will be some questions, and I will be able to maybe give some answers in this live stream. Um, okay, yeah, there is one question. Can you do microstructures in it? Right now we are in development of doing the microstructures in WLAM. Currently we can do microstructure analysis in LPBF module, but this will be upcoming. Uh, what defects can you capture with it? So as we have seen, lack of fusion can be easily captured. Along with it, porosity can also be done with high fidelity simulations. You can rely much more on the simulation data, but for initial analysis you can do some low fidelity simulations, but for porosity measurements you will need high fidelity simulations. Is that is the four-phase multi-phase physics applicable in WLAM model? Yes, as we have discussed, we are dealing with multiple phases that are involved: solid, liquid, like there is a transformation. There is also a gas phase involved through the shielding gas, and there is a vapor phase that you can visualize through the simulations. Okay. There is another question. Can we capture the Marangoni effect, and is multi-layer possible? Yes, that definitely is possible. Some Marangoni effect was already shown in the presentation, and for multi-layers, I think there was one scan strategy that showed multi-layer deposition. So yeah, it is possible. It totally depends on how much of the layers you want to have in the build and how much of computational power you have at hand. Defects such as balling porosity, lack of fusion. Grooves can be simulated. Okay. Do you perform stress analysis? This is one of the questions. So as for now, we cannot perform any stress analysis, but coming in the future, there will be a different module that will be attached in AM PravaH that can do this. Can we extract thermal data from LPBF to predict microstructure? Like for LPBF, it is possible. For WLAM, where we are working towards developing the microstructure module, so yes, it is also possible. How to procure the license? You can contact Paanduv Applications through the website, or just call us on the given number. The AM PravaH demo form can also be found in the description. So if you want a license and want a demo, like how the simulation software performs, you can fill out the form that is given in the description, and we will get back to you. Do you have student version of AM PravaH? Uh, as of now, we do not have any student license, but you feel free to contact Paanduv Applications for further reach, so that we can maybe provide this software to the institution where you are studying and maybe use it there. Is it possible to simulate extrusion based 3D printing like with metal polymer feedstock? Right now, we are only having metallic materials in the material database. Uh, for the extrusion based 3D printing, we will have to look into like the development of this module. What are the specifications required for configuration? You can run AM PravaH in Linux system, and depending on what kind of graphics card you have, you can have more computational powers. But for operation of AM PravaH, you will need Linux system. Yeah. So I think, yeah, these are all the questions. If you have any question, you can comment on this video later on, and someone from Paanduv Applications will get back to you. So thank you very much for your time, and you will hear back from us